Additionally, the findings of the JWST at the border of the observable universe force us to reconsider our understanding of cosmology, particularly the idea of inflation. The rapid expansion of the universe in the moments after the Big Bang, known as inflation, suggests that the universe expanded exponentially in the first fractions of a second, eradicating any irregularities and setting the stage for the formation of galaxies and large-scale structures. However, if the JWST finds unexpected anomalies or structures in these faraway galaxies, it could challenge the inflationary model. Physicists are being prompted to refine, or even overhaul, our current understanding of the universe's earliest moments. Beyond the cosmological implications, the announcement has philosophical and existential significance as well. The discovery of galaxies at the farthest reaches of the observable universe prompts us to ask fundamental questions about our place in the universe and what lies beyond the observable universe. Is there a multiverse, with countless other universes existing beyond our own, each with its own set of physical laws and conditions? Some theories suggest that the observable universe is just one bubble in a vast multiverse, with other bubbles existing beyond the cosmic horizon. If true, this would mean that the universe we see is only a tiny part of a much more expansive and intricate reality. These discoveries also highlight the limits of human knowledge and the scale of the universe. As we look deeper into space, we are reminded of how small and fragile our planet is in the grandest scheme of things. Yet, at the same time, the fact that we are able to observe and comprehend the universe at this level is a testament to the power of human curiosity and ingenuity. The James Webb Space Telescope represents the pinnacle of decades of scientific and engineering effort, and its discoveries will shape our understanding of the cosmos for generations to come. In addition to expanding our knowledge of the universe's origins, the JWST's observations at the end of the observable universe will likely have practical implications for the search for extraterrestrial life. By studying the first galaxies and stars, astronomers can gain insights into how the things that are necessary for life, like the presence of heavy elements such as carbon and oxygen, developed over time. This, in turn, informs our understanding of where life might exist elsewhere in the universe. While the stars and galaxies at the outer limits of the observable universe are too far away for us to detect signs of life directly, studying their formation can help us understand how common life-bearing planets might be in other parts of the universe. The announcement also underscores the importance of collaboration and international cooperation in advancing our knowledge of the universe. The JWST is a joint project of NASA, the European Space Agency (ESA), and the Canadian Space Agency (CSA). And its success is a testament to the power of global collaboration. No single country or organization could have built and operated a telescope as complex and advanced as the JWST on its own. The discoveries made by the telescope, including its observations at the edge of the observable universe, are the result of the combined efforts of thousands of scientists, engineers, and technicians from around the world. The James Webb Space Telescope's revelation of the most distant reaches of the observable universe does more than merely extend the boundaries of what we can see. It fundamentally challenges and reframes some of the most long-held assumptions in cosmology, astrophysics, and even philosophy. To grasp the full depth of what the telescope's observations mean, we must delve into the intricate and often bewildering details of how the observable universe works, what the telescope has shown us, and how those revelations change our understanding of not only space, but time, existence, and the laws that govern them. One of the most significant repercussions of the James Webb Space Telescope's announcement is its potential to refine or redefine the standard model of cosmology. The Standard Model describes the universe's expansion from the Big Bang, around 13.8 billion years ago, to the present day. Embedded within this model are assumptions about how matter and energy behave at vast scales, about the early universe's rapid expansion through inflation, and about the mysterious dark matter and dark energy that seem to make up the majority of the cosmos. The discoveries made by the JWST at the edge of the observable universe could force us to rethink these assumptions. The first stars and galaxies, those early structures captured by the JWST, are unlike anything we observe in the local universe. They are more massive, and their formation times may be much earlier than previously expected. These findings could indicate that the models we use to describe how galaxies form from clouds of gas might need adjustment. The conventional model suggests a particular time frame within which galaxies form, based on the cooling of gas and the clustering of dark matter halos. If the JWST is observing galaxies far older than this model allows, cosmologists may need to reconsider the exact processes that drove early galaxy formation. There are also more speculative theories about the universe that this discovery touches upon. For instance, there's the idea that the universe is a hologram. The holographic principle suggests that the entire universe can be described by information encoded on a two-dimensional surface at the boundary of the universe, similar to how a hologram encodes a three-dimensional image on a two-dimensional surface. This hypothesis comes from attempts to reconcile quantum mechanics and general relativity, especially in relation to black holes. While this theory is far from proven, discoveries that extend our understanding of the universe's outermost regions inevitably feed back into these theoretical frameworks. Perhaps what we think of as the end of the observable universe is not an edge, but a form of boundary where different physical laws or interpretations of time and space apply. The JWST's revelations about what lies at the limits of the observable universe intersect with debates about the nature of time. In Einstein's theory of general relativity, space and time are intimately connected, forming a four-dimensional fabric known as spacetime. The telescope's ability to look so far back into the universe's history means we are also looking into deep time, when conditions were radically different from the present. One of the more fascinating aspects of the James Webb Space Telescope's discovery is how it impacts our comprehension of the early universe's timeline. The early universe was filled with a hot, dense plasma in which atoms had not yet formed. As the universe expanded and cooled, it reached a point known as recombination, where electrons combined with protons to form neutral hydrogen, allowing light to travel without restriction for the first time. This event is known as cosmic microwave background (CMB), is considered the furthest point back in time we can observe. However, the galaxies the JWST has observed date to a time shortly following this period. In the epoch of reionization, when the first stars began to ionize the hydrogen that filled the universe. The data that caused this problem was gathered by the European Space Agency's Gaia satellite, which provides detailed distances and positions of nearly 2 billion stars in our galaxy. These findings have prompted astronomers to rethink their models of stellar behavior, especially when it comes to stars at the outer edges of the Milky Way. The speed at which stars move in these outer edges is an important factor in estimating the mass of a galaxy, as the gravitational force acting on each star depends on the galaxy's total mass. A recent study based on Gaia's data calculated the total mass of the Milky Way, including gas, dust, dark matter, and stars, as roughly 200,000 billion times the mass of our Sun. As long as this estimate stands, it is significant. It's about 5 times smaller than previous estimates. This discrepancy could indicate that there's less dark matter in our galaxy than previously thought. However, measuring the mass of a galaxy is an inherently difficult task, so there may be ambiguities in the data provided by Gaia or in the methods used to analyze it. We continue to stay updated with new discoveries in this field. If you enjoyed this video, please like and subscribe. We anticipate sharing additional updates in the future as we look further into these findings. It is important to consider that space exploration and cosmic observation are evolving fields. With each breakthrough, our comprehension of the universe deepens. The discovery of unexpected events in the universe, like stars potentially older than the universe itself, demands that we confront the limitations of our current theories. This ongoing journey invites a re-evaluation of fundamental concepts in physics and astronomy, challenging us to keep refining and expanding our understanding. In addition to these revelations, astronomers and physicists are also investigating other aspects of cosmic structure and behavior, such as the distribution and interaction of dark matter. Dark matter, which cannot be directly observed, is thought to constitute a significant portion of the universe's mass. Its elusive nature has sparked numerous theories, each carrying different implications for the structure and formation of galaxies. Some scientists speculate that the absence or reduced presence of dark matter in certain regions of space could help explain unexpected observations, like the slower movement of stars in the outer parts of the Milky Way. The intricacies of these studies are made even more complex by the fact that much of our current data is based on indirect observations. Instruments like the Gaia satellite provide precise measurements, but interpreting this data is fraught with complications. The position and movement of stars, especially in outer galactic regions, are affected by a wide range of factors, making it difficult to isolate the causes of observed behaviors. As researchers continue to gather and analyze more data, we may uncover new patterns that could shift our understanding of galactic evolution. One of the most exciting prospects of this ongoing research is the potential for a paradigm shift in our conception of the universe's age and structure. If the theories proposed by Professor Gupta and others hold any weight, it could revolutionize our understanding of the cosmos, possibly placing the universe's true age as much older than we've previously thought. The implications of such a shift are profound, altering our perspective on the nature of spacetime, the laws of physics, and the history of cosmic events. Additionally, advances in observational technology, such as the James Webb Space Telescope, let us look further into the past, examining distant stars, galaxies, and cosmic phenomena with unprecedented clarity. These advancements are opening new frontiers in space exploration and pushing the boundaries of what we know about the universe. The possibility of discovering ancient celestial objects that challenge our existing models is an exciting prospect that continues to inspire curiosity among scientists and enthusiasts alike. The debate over the true age of the universe also prompts broader questions about the nature of scientific inquiry itself. How can we reconcile opposing data? How can we modify our models in the face of unexpected discoveries? The pursuit of knowledge in cosmology is ever-changing. Discoveries made by NASA, the University of Ottawa, and others highlight the dynamic nature of scientific exploration. Each new finding not only adds to the mystery but also brings us closer to unraveling the truths that govern the universe. As we continue to explore these questions, it's essential to remain open to the universe's possibilities. With all its vastness and complexity, it might hold answers we haven't yet imagined. Perhaps the real mystery lies not in the stars themselves, but in how we interpret the data and theories that emerge as we push the boundaries of knowledge. The future of cosmology holds great promise. As we unlock new layers of understanding, we will inevitably gain more insight into the true nature of the universe. In conclusion, while the questions surrounding the age of the universe and the existence of ancient stars present intriguing puzzles, they also offer an exciting opportunity to expand our comprehension of the cosmos. We must continue to question, explore, and refine our models of the universe as new discoveries emerge. Whether the universe is 13.8 billion years old or potentially older, each new discovery adds a piece to the puzzle, guiding us toward a deeper and more profound understanding of the universe's origin, structure, and future. Stay tuned for more exciting revelations, as scientists around the world work tirelessly to uncover the mysteries of our vast universe. As scientists continue to study the cosmos, it is clear that every new discovery brings as many questions as answers. The complexities of cosmic phenomena, like the ancient star HD 140283 and the age of the universe, challenge our current scientific models and force us to reconsider the very foundations of cosmology. Each discovery opens the door to new theories and interpretations, prompting researchers to revisit their long-held beliefs and assumptions. A particularly intriguing aspect of these recent findings is the potential for a significant revision in our understanding of the universe's timeline. If the universe's age is indeed closer to 26.7 billion years, as suggested by Professor Gupta, it would mean our previous calculations were too conservative. This new estimate, though controversial, could have profound implications not just for cosmology but for other branches of science as well. It may offer answers to fundamental questions about the universe's origin, the nature of dark matter, and the forces that drive cosmic expansion. One key factor in the ongoing debate is the concept of dark matter, which is thought to account for a substantial portion of the universe's mass. Dark matter is invisible and interacts with regular matter only through gravity, making it exceedingly difficult to detect. However, its presence can be inferred from its gravitational effects on visible matter, such as the rotation of galaxies. The idea that dark matter might be less abundant than previously thought could explain some of the anomalies we observe, such as the slower-than-expected movement of stars in the outer regions of our galaxy. The Gaia satellites data, which provide detailed measurements of the positions and motions of billions of stars, has led to a reconsideration of the Milky Way's mass. This new evaluation estimates the galaxy's mass to be roughly 200,000 billion times the mass of the Sun, challenging earlier models that placed the Milky Way's mass much higher. If dark matter is less abundant than scientists have assumed, this would force a significant revision of our understanding of galactic structure. However, the procedure for measuring a galaxy's mass is fraught with uncertainties, and scientists remain cautious when interpreting data from these new findings. In addition to these intriguing revelations, there are also broader philosophical questions at play. As we learn more about the universe, we are constantly confronted with the limits of human knowledge and the need to remain humble in the face of the unknown. The pursuit of scientific understanding is not just about finding definitive answers, it is about asking the right questions and embracing the uncertainty that drives discovery. With each new breakthrough, we are reminded of how much there is still to learn and how much more remains to be explored.